And here's the third one, and we call this the general method. And this one's slightly different. Actually, I might write it over there because I need more room for this. The key with the general method is recognizing, right, that the solution to the square roots of negative 36 are not going to be real. We already know what they are, okay? But let's suppose we didn't. So we want to find the square roots. We can use another value, right? We could use of negative 64. And yeah, we know that that would be plus or minus 8i, okay? Using this kind of identity. But let's suppose we didn't. Let's see if we can construct a general equation to make this work. And go back to James's definition. What did he say, again, was the definition of a square root? He was saying, can you tell me again, just to remind me?
The number that you can times together by itself to find the original number you wanted to find the square root of.
Right. So basically, if I multiply two numbers together, I'm going to get negative 64. Is that right? That's kind of what you're saying, yeah? So let's suppose we know that these aren't real. We know that the solution to this has to be some complex number z plus yi. How would we use James's definition here? What would be on the other side of this equation if I know that there's some kind of complex number that needs to satisfy this? Yeah? This square, right. So does that make sense, right? Where James is saying, okay, I need to multiply this number by itself to get negative 64, so I can write that as x plus yi all squared, right? There is some value for x and y which satisfies this, yeah. The question is, how are we going to solve for this? I don't know if can anyone see a problem with trying to solve for x and y in this equation? There's two variables, one equation. And I always tell you that if you want to be able to solve an equation, you need to have as many variables as you have, you need to have that many equations. So what are we going to do here? It's not immediately clear what we need to do, but I'm going to tell you that if we expand it out, we can start to get an idea of what to do, right? Let's go ahead and do that. So negative 64 is equal to, well, this is just a kind of perfect square, right? So we get x squared plus 2xyi plus y squared I squared. And we know that this guy here is just going to be negative 1. Well, I suppose it's just going to be negative 1. And when I write it in a different way, I'm going to put this over here. I'm going to kind of just rearrange it within itself. So we have x squared minus y squared plus 2xyi. Now I want you to have a think. There's a particular reason why I've done that. I wonder if anyone can see why. See, we'll go back to the problem, right? The problem is we have one equation with two variables. What I want to be able to do is I want to be able to have two equations so I can actually find the value of these two variables. Yeah.
The x squared minus y squared is the difference of two squares? So
it is a difference of two squares. So, well, you could do x plus y, x minus y, kind of. Is that what you're thinking? That's definitely an observation, yeah? It is the difference of two squares. Again, we want to be thinking things that lend us to creating two equations somehow out of one equation, which if I did kind of factorize that, it definitely does something. But unfortunately, it doesn't get us into the right direction that we're thinking, that we need to be going. We need, essentially, basically, we need two equations from the single one equation. And the hint is that you have some tools that you've learned before that can actually create two equations out of one from this topic. Yeah, conjugates?
yeah.
What?
I don't know.
Conjugates find we change the sign of the imaginary part. That's a bit of a clue, actually, the imaginary part.
Like, because there's like two cases.
What are the two? What do you mean two cases?
Like a positive and negative case on that.
For a square root?
Isn't that being two real parts in a complex number?
What are the real parts of this complex number?
Yeah.
Let's write it differently. Let's take this idea, right? Negative 64. Does this have an imaginary part?
Yeah.
What is it?
2xy.
Oh no, what about this one? This
Oh,
one?
sorry.
No, not like it does, yeah.
Zero.
What is it? Yeah, it does. Everything has an imaginary part. It's just that often the coefficient is 0, right? So you're going to get 0i. wonder if that helps us at all.
Yeah.
How does it help?
Well, obviously it helps us because I wonder. Alright. Do some stuff.
The goal of this at the end of the day was, we have one equation and I want to construct two. And it's not immediately clear how I do that. But I've written this in such a way, because here I've got some real part, and here I've got some imaginary part. And in between them I have an equal sign, right?
I get what you mean now.
So what are you thinking?
So, negative 64 has to equal x squared minus y squared, and 0 has to equal 2xy.
Remember, it's a very simple thing, equality, right? We take it for granted. We just say, yeah, two things are equal. So, I mean, obviously they're equal, they're the same, makes sense. The great thing with complex numbers is when you're saying two complex numbers are equal, you're actually saying a bit more than that. You're saying that the real parts are equal and the imaginary parts are equal. And what that allows you to do is to develop a general method for finding square roots of any number, not just negative real numbers. We're going to do complex numbers in a moment, right? But like Matt realized, we can actually say, okay, well, if these are equal, we can, and again, this is the emphasis on using like English to tell people what you're doing. We can equate real and imaginary parts. And this is when like defining arithmetic allows you to do more than just create definitions. It allows you to actually solve problems now, right? If we equate real and imaginary parts, we've got our real parts here. We've got our imaginary parts here. So we know now that x squared minus y squared equals to 64, and 2xy is equal to, what is 2xy equal to? 0. And this is why when we're talking about the parts, right, particularly for the imaginary parts, I'm actually only talking about the coefficient there, right? The I value, yeah, that's the imaginary unit, but the part itself is just the value that's in front of it. So now we have simultaneous equations here, right? And just as a bit of a disclaimer, in advance, you generally see that simultaneous equations are a skill that is examined to see if you know how to do it. In Extension 2, simultaneous equations are more of a tool to allow you to just solve problems. So in saying that, we don't necessarily need to kind of work this out as clearly as you would for an advanced kind of like question. Why do I say that? Because some of these you can actually solve by observation, right? But we can go ahead and do it. Like, well, how would you do this? Normally you do potentially like substitution, right? You could say x is equal to 0 or y is equal to 0. And if you do that over here, what do you get? Yeah, and I'm actually going to show you this very clearly because there's something very important that I didn't write over here. If we take, for example, sorry, this should be negative 64. If we take, for example, let's take x is equal to 0. So if we got x is equal to 0, I'm going to not have enough space for that. Let's do x is equal to 0. We get negative y squared equals to negative 64. Y squared is equal to 64. So y is equal to plus or minus 8. Okay. All right, and that's kind of our answer, yeah? So when x is equal to 0, y is equal to plus or minus 8, which means if we go back to this, our complex number here, the one that satisfies this, is going to be the square roots plus or minus 8i, yeah, which is what we expected because we already knew that, yeah. But then hang on, what about if y is equal to 0? Do this in red. If y is equal to 0, what are we going to get? We're going to get x squared is equal to negative 64. So what are the solutions to this one? Hang on, so apparently if y is equal to 0, x equals to plus or minus 8i. And does that work if we go back? Kind of, right? If we go back to here. But there's a problem with actually doing this. And it's a problem with when we define what a complex number actually was. And I said this was kind of built into the assumptions anytime you define a complex number, right? It's that these variables here, x and y actually have to be real values. Okay, so that's a condition that's applied anytime you define a complex number z. X and y here, they're real values here. So this solution, we're actually going to reject. Yeah, we don't consider it because of the fact that x and y have to be real values here. Yeah. So, yeah, it is a bit mean, isn't it? 3 methods to find square roots of negative real numbers. Which one do we prefer the most? Sorry?
I don't remember. C.
Which one do you reckon is the quickest?
Probably observation if you got a simple one.
Yeah, probably observation if you have a simple one, right? And I completely agree. Anytime you have a negative real number where you can just observe it, you need to think about the most efficient way to do that. And that's definitely going to be using this.
That's probably going to be what we have to use eventually.
And this general method is very powerful, right? Because what it allows you to do now, it allows you to find the square roots of any complex number.